Hi, I'm Nashijia. To determine optimal number of elements, we can use conversion test. Based on the graph, we found that the displacement at point B in x direction increased as the number of elements increased. The optimal number of elements can be said is 533 as the value of x directional displacement increase and start to converge at that value approximately. After that, we compare the displacement, stress, and strength in both x and y direction for both cases, which is 15 elements and 523 elements are used. We found that the displacement, stress, and strength at point A, B, and C are different when we're using different number of elements. This is because the entire geometry of model will have a slight change when we increase the number of elements. So the optimal number of elements is the best option for us to determine the most accurate result. Besides, we also can compare the both cases from the error calculated by, by calculating the difference of value for both cases. And we found that the error between both cases are relatively small. Next, we can determine Poisson ratio using the formula of taking longitudinal strength divided by transverse strength. We're taking the normal strength at point B when optimal number of elements are used. As I said before, optimal number of elements will give us the most accurate result, and we get the Poisson ratio is equal to 0.2806. In this project, theoretical Poisson ratio given is 0.3. Hence, the percentage error is 6.47%, which is relatively small error. Besides, we also can determine stress concentration factor Kt using the formula given sigma max over sigma naught, where sigma max can be obtained directly from analysis results. Sigma naught we need to calculate manually using the formula F over dt. F is the force applied, d is the dimension of plate d, t is the thickness of it. Since the project given directly the R per D and W per D both two ratio, so we can obtain the theoretical KT from the graph, which is 1.7. In this analysis, we assume the plate is exerted axial force of 100 Newton. Noted that the 100 Newton is applied on a quarter plate. So for full model, we need to times 2, become 200 Newton. And the dt is the value we assume. And we get the sigma naught equal to 0.4 megapascal. One of the observation we have is the maximum stress always occurs at point C. For 50 elements used, we obtain that the sigma max is equal to 0.65715 megapascal. For 523 elements are used, we found that sigma max equal to 4.81080 megapascal. After that, we calculate the Kt for both cases using the formula sigma max over sigma naught. And we obtain that the Kt for 15 elements is 1.64. The percentage error is 3.53, relatively small. For 523 elements, we obtain the Kt is 12.03, and the percentage error is quite big, over 100. This is maybe due caused by inappropriate assumption we made in the previous analysis. In conclusion, the objective of this case study is successfully achieved. By using the same structure, boundary condition, and loading, the deformation and stress can be obtained manually by using finite element method with the assist of Octave programming software. The other deformation and stress analysis can be also carried out using ANSYS software. Besides, ANSYS software can help us to do a simulation so we can know the condition of the model clearly. The comparison of both methods come up with similar outcomes and give minimal deviation percentage. The optimal number of elements in this study is 523 elements. It is obtained by multiple analysis in ANSYS software and by using the method we call convergence test. That's all for my presentation. Thank you for your attention.